Okay, more physics. We are on page 140, and this is overcoming friction. So if you'd like, turn to page 140, and what I'm going to do is practice. I'm going to do practice problem. This is practice problem. Look in E. This is number 1. Practice problem number 1. All right. Overcoming friction. That's the title. Got it? All right. So here's the scenario. Here's the system. A student pulls on a rope attached to a box of books, moving the box down the hall. The student pulls with a force of 185 newtons at an angle of 25 degrees above the horizontal. The box has a mass of 35 kilograms, and the coefficient of friction, or the mu sub k, is 0.27. What we want is acceleration. Make a long story short, we know the applied force, which is 185 newtons at 25 degrees. We know the mass, which is 35 kilograms, and we know the mu sub k, which is the coefficient of friction. And you picked that up last time on the last video, what mu sub k is. So the first thing we should do is we should start with a free body diagram. This gives you an idea, but it's not technically a free body diagram, because I think a coordinate system, what it does is the coordinate system gives you a good idea of what's happening in the x and the y directions. So this is the y direction, and this is the x direction. All right. So this dot we'll assume is the center of gravity, and this will help us. And let's identify the force going in the negative y direction would be the force of gravity. So this would be negative force of gravity, and we can decide that this is negative and this is positive. It's not like there's a law, but we're going to say that's negative, and we're going to say that the normal force is positive. So this is the positive force, which is the normal force. Then we're going to have some friction force going in the negative direction. So this is going to be force of friction in the negative direction, and then we're going to have an applied force, aren't we? And hopefully the applied force is greater than friction force, because we need acceleration, and then we're going to need some movement. So I exaggerated it just slightly by making this vector longer, but you get the point. This vector has to be longer. These two vectors we assume are about the same size, because it's not going in the up or down. It's not going up or down. It's just going in the horizontal. Anyway, this vector here, we're going to have to get as a result of resolving this vector. So remember, this angle here, this angle we said is 25 degrees. So we've got a 25-degree angle that we're going to have to deal with, and that's not a problem. We've done that. We've done that loads of time. So there's basically what we're going to have to do is we're going to have to remember that we have these opposing forces in the x and y direction. And if you think of it in this system, I think it'll help. All right. So let's start with the first step. Our first step is to find the applied force in the x and the y direction. All right. So we're basically going to resolve this vector. Force y applied equals the sine of 25 times 185 newtons. And then that equals 78 newtons, and then we need the force in the x direction applied, which is the cosine of 25 times 185 newtons, and that's going to be 167 newtons. All right. Now that's our first step. So we're gonna need that. Remember this is going in the east direction and this is going north. All right. So both of those are positive. That's our first step. Okay. Second step is that we need to find the normal force. All right. We need to find the normal force. Now, in order to find the normal force, what we need to do is we need to take all the forces in the y direction. All the forces in the y direction are going to be the normal force plus the force applied in the y direction, which we just found, and we're going to have to add that to the negative, the force of gravity. We basically need to subtract it from the force of gravity because all that is equal to 0 because we know that it's not accelerating up and down. So we have we know the force of gravity because I guess I need to throw in here 2 sub a step, huh? Step 2 sub a. We've got to find force of gravity. Remember, that's just mass times acceleration. So that's going to be, we know that the mass is 35 times 9.81. So that's going to be 343 newtons. So we know that this is 343 newtons, and we know that we just found this, which we said was 78 newtons, right? So we've said that all this equals 0. So this plus this has got to equal 0. So just subtract that from that, and we should get F sub n, which is the normal force, is going to be 265 newtons. All right. So we need the normal force. Right? So now that we have the normal force, we're ready to go on to step 3. Now in step 3, we have to find the force of kinetic friction. It is moving, so we know it's kinetic friction. Find the friction, and it's kinetic friction. And the way we do that is force of kinetic friction equals mu sub k. That's an awful big subscript. Mu sub k times the normal force. So we've been given mu sub k, so that's nice and handy. So all we have to do is we have to say 0.27 times 265 newtons. We just found this whenever we said that the F sub n is 265. Remember, we just found that. Okay, so that's easy enough. And then if we multiply this, then the force in the kinetic friction force is 71.5 newtons. So that's important. And then now let's just wrap this up to step 4. Now that we know the friction force, the force in the x direction, which is our concern, because force in the x direction is where we're going to get the acceleration, and that equals the force applied minus force applied in the x direction minus the friction force, and that's kinetic friction, equals mass times acceleration. So force times mass times acceleration. So we have 167 newtons minus 71.5 newtons equals 95.5 newtons. And then we needed the net force, and so now that we have the net force, we just have to rearrange force equals mass times acceleration and put the force over the mass to get the acceleration, right? And so that's easy enough. Now it's 95.5 newtons divided by the mass, which we've been given, which is handy. Right, so that's part of our known. We know the mass, so that's easy enough. And now we just we say that it's 27 meters per second squared.